There we go. I didn't have my tablet, so I had to get that. Alright. Welcome back to Chem 121. This is the last week of classes. So what we have on the agenda is basically, there's an exam at the end of the week, so that's on Friday. Make sure that if you want to take your exam on a different day, you can arrange that. You have to email me. If you email me before, like, 3 a.m., that was when I got around to doing all of the exam requests that I had already received because my internet was out until around then. And right as I was about to go to bed, it came back on, so I was like, oh, I'll just do this really quickly so that I can check it off my list. So I got all this done last night. But if you email me after that and you did not get a reply from me that says, okay, I did it, let me know if something isn't working, then I will get to that later today. If you have a request, make sure that you email it to me. Remember that Thursday is also available, as is Saturday. If you don't want to move your exam and you're happy to take it on Friday, don't do anything. It will open on Friday automatically. Quiz number 8 and quiz number 9 are due tonight. They will close tomorrow, and after they close on Wednesday, I'm going to open them all up for you so that you can see them for your exam number 2 on Friday. So that you can have them to study through Thursday and a little bit of Friday if you need to. Course evaluations are still open, so make sure to do that too. Those close, I think, at the end of the week. I'm not sure about that. Make sure you get them done, though, because, again, remember, if I get a significant number of responses, I will give everybody extra credit, and that is great. What else do I have? There is one more lab. The lab is about solubility. We've pretty much talked about solubility already in Chapter 8. So not super much to really say about that lab. I will open that assignment. It's due next week after the final. So sort of a one last thing to do before you go. And yeah, that's really it. So we're very close to the end, which is great because I am so ready to be done. It is finally summer and I want to go outside. Like, I actually see the sun today. It looks nice. Last week I was sick towards the end of the lecture and, like, really struggling, so I had to end the lecture a little early and call the doctor, which I am doing much better now, actually. So I had a severe sinus infection that day it had gotten worse, so I got an antibiotic and it actually worked a lot. I am like 95% of the way better now. But the consequence of that was that I didn't quite get through everything that I wanted to, and it turns out I wouldn't have anyway. So I asked you to watch a video on equilibrium. Hopefully you've done that, because we're going to start today with Chapter 10, and the equilibrium stuff is on quiz number 9, so be sure to go back and watch that video that I've put in the playlist in case you haven't. Chapter 10 is about acids and bases. And all of this is pretty important, so we're going to try and get through all of it, but it's kind of short and it's not terribly difficult. So, all right. What are acids and bases? So first we're going to talk about acids. We're going to define an acid as something that has the following properties. So the first one is, they taste sour. Blah. Acids, when you consume them, have a very sort of sour, tangy or tart taste to them. So if you've ever had, like, I don't know, a lime or a lemon by itself, or grapefruit, very sour, right? It's very tart. It's very, like, it bites, it feels like, when you taste it. Acids have this property. So the acids that are in things like lemon and lime are citric acid. And high enough concentrations of that, it starts tasting less like a fruit and more like just sour. What else can acids do? Many acids will dissolve metals and react with them. So for instance, nitric acid will react with copper to dissolve it to produce a blue solution, which is what you see here. The nitrogen becomes nitric oxide, which is a brown gas, which escapes. So be very careful when putting pennies in acid, because they may dissolve and produce the brown gas of awful. If you have a special piece of paper called litmus paper is designed to serve as a pH indicator, or it tests whether a substance is acid or basic. Now, some litmus papers are specifically for either an acid or a base. So blue litmus paper is specifically to detect the presence of acids. Blue litmus paper will turn red if dunked in an acid, as you can see here. Finally, acids are the counterpart of bases. Acids will neutralize bases so that neither remains. They react with each other. Now, what are common acids that you see every day? The most common acid by far is your stomach acid. You have hydrochloric acid in your stomach. It's fairly concentrated because it can cause burns if you like throw up, for example, or if you get acid reflux. You feel it in your esophagus. It causes a chemical burn, and it's not great. Other acids that are important, both industrially and commercially, are things like citric acid in fruit, but also other stuff like phosphoric acid. Phosphoric acid is added to soft drinks to give it a very tangy, tart taste. So Pepsi, for instance, has phosphoric acid in it. Other acids are useful industrially. So, for instance, lead acid batteries require sulfuric acid in order to be one part of an electrode so that it can hold and move a charge through it. Here's some examples of different acids that are useful in industry. I forgot my favorite acid. It's right here, carbonic acid. This acid is what's present in fizzy drinks, such as delicious polar seltzer. Cranberry lime. I'm almost out of it. I have to go get more. But the rest of these are fairly common. Acetic acid is vinegar. So if you have vinegar at home that you use for cooking, I mean, I don't know what else you'd use vinegar for, honestly. The majority active component of vinegar is acetic acid. Now, the majority component itself is water, but the second most abundant compound in vinegar is acetic acid. I don't really have much to say about these other ones. All right. The common feature on acids is you might notice that they all start with H's. So I'm going to circle the H's. So, well, this one is just this, but that are relevant to us here. And you'll notice that I'm not circling all of them. The reason for this is because in an acid, H plus will fall off of our substance. So, for instance, I would have H plus, and then, oh no, I mean, no, we would have nitrate. I hate when my tablet does this. I'm convinced that this is a Photoshop, or not a Photoshop, but a PowerPoint problem. There we go. So when we put our acid in water, one of the components that will pop off is H plus. The other one is whatever the other thing is left over. But not every H will do this. H will pop off if it is bonded to something that is very, very electronegative. The reason being, remember that we said in a bond that electron density is shared unevenly, and it's moved towards the electronegative atom. Well, if the difference is really big, then what ends up happening is that all the electrons eventually will make their way over there, and then H plus will just pop off as a proton. And so, instead of having a covalent bond, we end up with this. Now, again, this will only happen in locations where H is bonded to something that's very electronegative. So, for instance, oxygen would qualify. So you'll notice that all the H's bonded to O's are circled, but the H's bonded to carbons are not circled because carbon's not electronegative enough. Carbon holds onto its hydrogens. It likes hydrogen. It wants to be buddy-buddy. Oxygen, on the other hand, doesn't give a shit about hydrogen. It just wants its electrons. Now, will every oxygen do this? Not necessarily. We have to analyze and assess the acidity of a compound on a case-by-case basis. That's an acid-base pun. But we won't know if something is acidic in terms of the hydrogen coming off of the molecule until we do the experiment. We can make predictions, though. Part of this chapter is going to be making predictions about that to see what things happen. This group that I have circled here is relevant for organic chemistry. If you are taking Chemistry 131 next quarter, you're going to learn about different functional groups, of which this group is one of them. C double bond O, OH. So we've got C double bond O right here, OH. This is called a carboxylic acid. Carboxylic acids are very important in various synthesis. They are also important for amino acid reactions because the carboxylic acid group is the acid part of amino acid. Yeah, that's about it. All right, let's talk about bases. What does a base do? Bases do all the opposite things that acids do, although there aren't really opposites when it comes to like reacts with metals. They just react to something different, right? So let's go over those. So first is that bases taste bitter. Blah. If you have ever had medicine that tasted like super bitter and it just stayed on your tongue, then you've probably had a medicine that is basic. I don't know how many questions are on exam 2. Not off the top of my head, sorry. What else can bases do? Bases are slippery. If you touch bases, an interesting thing happens is your skin will feel very slick after you've done that. So maybe you've used soap and how do I want to describe this? So if you use soap, like if you wash like with a soap bar on like say your arm, and then you rinse and you like then run your thumb across it, depending on what soap you have, it might leave like a little residue. And what that residue is, why is there a cat meowing behind me? Hold on. Maya, please. Sorry. Okay. What that residue is the soap that is reacting with your skin that causes it to dissolve. I was hoping that would be a little louder, but it wasn't. That's okay. Yeah, so basically when you are washing yourself with soap and water every time you shower, I almost said every morning because that's when I shower, but if you shower at night, you're also valid. What you are doing is literally dissolving your flesh. That's okay because the outermost layer of skin on your body is dead anyway, so we're fine with getting rid of that. But bases are slippery because they are reacting with fatty acids, of which there are fatty acids on your skin. What else can bases do? Well, they react with litmus paper. The color of litmus paper that we have for a base is the red litmus paper, and it turns them blue. So acids are red and bases are blue. Sugar is sweet and chemistry is too. I don't know. Bases are also capable of neutralizing acids, as we kind of expected. Bases are not as common in food. Acids are very common in food, and we've sort of acclimated to them. Most bases are toxic or because our senses have evolved in such a way to recognize, oh, that's basic, that's probably dangerous for us. That said, some bases do exist that we have sort of appropriated into culture, such as caffeine from either coffee or dark chocolate. So cocoa is extremely bitter. And the reason for that is because it contains caffeine, which is a base, but also contains other bases too. What we do is we fill it with sugar and milk and other things, and then we have like a really delicious, yummy thing. Caffeine, same way. If you drink straight coffee with no sugar or cream or anything like that, it's very bitter, but some people like that. All right. What else can we do with bases here? Well, we could do nothing because nothing is happening when I click. There we go. The most common use of bases is that they're very good at saponifying fatty acids. That makes them very good at cleaning because they will react with things that are fatty or greasy and they will make them soluble. And you're going to explore a little bit of that in lab number 5, which I will put the assignment up after classes later today. In fact, to make soap, you need to put bases into your mixture. In the past, we have made soap in the laboratory when we were doing these classes in person. And what you do is you add sodium hydroxide, which is a very strong base, to a sample of some sort of oil, so like coconut oil or olive oil or some sort of oil that you can use, and then you boil the heck out of it in the presence of the sodium hydroxide. And what it ends up turning into is a chunky solid because the oil has been saponified. You'll learn more about saponification in Chem 131. Here are some common bases. Bases are mostly going to be important for cleaning. A common medicinal use for bases is in the treatment of indigestion or stomach troubles. So if your tummy is rumbly because you ate too much or you've upset it somehow, one of the things you can do is you can take sodium bicarbonate or sodium carbonate or calcium carbonate, one of those 3. On the screen here, you can see these antacid tablets. These are calcium carbonate. Calcium carbonate is this insoluble, chalky white solid. In fact, chalk is calcium carbonate. But if you eat Tums, what ends up happening is the calcium carbonate dissolves into your stomach in the presence of acid. The carbonate then reacts with the acid to become hydrogen carbonate. And then it bubbles out as CO2, leaving just water. So it effectively neutralizes the acid. Now, the last base down there is actually really important, ammonia. We're going to talk a lot about ammonia later on. Because ammonia does something that these other substances don't do. And that is, well, there's no H's in here connected to O's. So how do I know how this acid-base relationship works? In fact, it's the first base that we introduce nitrogen with, and we're going to talk about what that means in a little bit. We're going to define acids and bases in 2 different ways. The way that we're not going to cover is the Lewis method. So this is not something that we're going to define in this class. It deals with electrons. We're going to use 2 other methods because they're good enough for your purposes. The first method is just kind of it's all right. But this method is going to be the one that we care about. So let's talk about the Arrhenius definition because it's a good starting place. It's just incomplete. That's the problem with it. The Arrhenius definition of acids and bases cares about things that the molecules have. And those things are the following. Acids have H+, bases have OH-. In both cases, the substance dissociates into 2 pieces. one of those pieces has to be this for it to be an acid, or this for it to be a base. There you go. So now you're just going to be looking for substances that have H's that will pop off, or hydroxides that will pop off. And you can see if we go back here, like, oh yeah, I could see, you start seeing OHs everywhere, right? And then you get to this and you're like, huh? How does that work? And we'll solve that later. So that's what our mission is going to be. Look for things that will dissociate into H plus or OH minus. If my substance is an acid, here's what happens. Boop. That's pretty straightforward. We already showed that with the Lewis structure where I said, okay, well, here's my HCl. I'll actually draw the electrons in this time. I'm just going to shuffle all the electrons over there. And there you go. So, great, that works out nice and well. Now, what is this? Hydrogen only has one proton and one electron, but if I make it positively charged, it doesn't have any electrons at all, does it? So, therefore, H plus is just a sad, lonely proton floating around. Acids are protons, and because acids taste sour, congratulations, you know what protons taste like. Isn't that weird? Chemistry is silly sometimes. Hi, I'm in the nucleus. I taste sour. Fun fact. And it's true. H plus is literally just a proton. Protons are extremely tiny, and they're also very charged. They have a charge of +1. In water, that's not going to go unnoticed. And so what water will do is, because it's polar, it's going to be attracted to H plus, and it's going to end up scooping them up. Water becomes its chaperone. And what ends up happening is we get this. We get H3O plus, which is called the hydronium ion. Now, chemists will interchangeably use H plus and H3O plus to mean the same thing. So these are equivalent to U. Both of them mean, oh, an acid is dissociated and the H plus is represented by this thing, whatever that thing might be. So don't be afraid if you see either of those terms, because depending on the class and depending on the context, you'll see one or the other. All right. What do bases do? Well, bases dissociate in water as well. If I have a base like this, it will split into two pieces. There's one piece, there's the hydroxide. Note that hydroxide has a negative charge, which you should remember from your polyatomic ions back at the start of like chapter 6 or 5 or 4, I don't know, wherever it was. It was a long time ago. The other ion that pops off is whatever that metal would be. So if it was sodium, it'd be Na+, potassium is K+, and so on. Now, all Arrhenius bases have hydroxide, so therefore they are all ionic compounds. So it's very easy for them to dissociate in water. Now, if I combine the acid part and the base part, this is what happens. H plus OH neutralizes both the charges and the acid/base. I make water. Hooray. If I was representing it in this manner, then I'd make 2 water. Ooh. Now, if you're thirsty, this is not an efficient way of creating water. because you need a significant concentration of acid and a significant concentration of base, and the reaction of both would probably boil the water. One common experiment that scientists like to do for unsuspecting young chemists, I guess we'll say, is that they'll take a beaker of hydrochloric acid, like super concentrated, it's literally steaming, and then sodium hydroxide, which is very caustic. They'll pour both of them into a larger container, shake it up, and drink it. I had a instructor do this as one of my first reactions in high school. He went up to the front of the room and slammed the glass bottle of HCl down on the counter. Makes a big thud. We think he's gonna break it. The sodium hydroxide bottle is this plastic jug that just has skulls and crossbones over it, and he pours both into beakers, carefully measured, thankfully. Mixes them together, and then down the hatch it goes. And he goes, "What did I just do?" And we're just all like mortified by this. And he's like, well, "I drank salt water." And then he writes the reaction on the board. He drank salty as hell water, probably, because of 14 molar HCl being neutralized by 14 molar sodium hydroxide. So there's our Arrhenius definition, but we have an issue. And the issue is, how the heck do I fit a base like ammonia in here? Now we know it's a base because if I take red litmus paper and I put ammonia in it, it turns blue. And that is literally where the term litmus test comes from. So how the heck does this work? Turns out ammonia does this. This is what ammonia will do in solution. It will produce hydroxide by reacting with water. The ammonia itself doesn't produce a base, but we say that it is acting as one because it just leads us down the chain of command here. So, because this produces a base, we're going to just call this a base too. But we need a way to define this that doesn't require us to look at something as some part of its structure. So there's nothing in ammonia that's super identifying as, oh, it's a base. I mean, it's got nitrogen, and most nitrogen-containing compounds are basic, it turns out, but not all of them. So let's look for a better definition. And fortunately, Bronsted-Lowry are able to do that. So we have changed the definition of acids and bases from the Arrhenius definition to this, the Bronsted-Lowry definition. It's more complete. And here's the Bronsted-Lowry definition. Bronsted-Lowry acids are any substances that donate H plus the solution. So here is my I don't know, I was just writing some acid here. So here's my acid. If it dissociates, this happens. I have added H plus to the solution. Therefore, the substance I was looking at was an acid. All right, what about a base? A Bronsted-Lowry base removes H plus from the solution. Like we said before, bases do the opposite thing that acids do. If acids add H+, bases will remove it. So something like this can react with H+, absorbing it from the solution. And I've already screwed that up. Hold on. There we go. If we remove H+, we are a base. So anything that will react with H+, so that it is no longer in solution, is a base. All right, so now that we've got these definitions down, what we're going to do is we're going to start assigning these labels to things in a reaction. For instance, here, if I have HCl reacting with water, HCl is giving its H to H2O. So what we would do is we would write this. HCl is an acid. In this circumstance, water here is accepting an H plus from the solution and is going to keep it for itself. So water is acting like a base. Now, the result that we get is still an acid over here. And if this H plus could react with Cl minus, we would call this a base, and then the reaction would reverse. But we can see that the reaction isn't reversible. Make sure to review reversible reactions in the equilibrium lecture that we didn't get to do on Thursday. Now, if we look at this from the perspective of ammonia, and I write that down right here, here, ammonia is taking a hydrogen from water, which means that water is donating the hydrogen to the solution, which makes it the acid, and ammonia is the base. Now, interesting, water did both things here. Excuse me. Can something be both an acid and a base? And the answer is, yeah, it's all relative, right? For example, let's suppose that I was looking at how strong somebody was. I can lift a certain amount of weight. So maybe, like, among all my friends, I'm very strong. Because I can lift 120 pounds or something like that, and they can't. However, if I go to the gym, 120 pounds is real weak, so I'm weak compared to them. With acids and bases, it's sort of the same way. If something is not a strong enough acid relative to other things, the thing that is the stronger acid will be the one donating the H plus, and other things are forced to accept it. So, water in this case is a very weak acid, but it's also a very weak base, so it sort of gets bullied around and just does whatever it's told. We're going to see that as we go through this these examples here. So, looking at this example here, let's label things as acids or bases. We're going to stay to the left side of the arrow for now. We'll talk about the right side of the arrow in a little bit. But what I want you to do is I want you to identify what is what behaving as for this reaction. So 1 and 2, type your answer in the chat there. Tell me what's an acid and what's a base for this reaction as written. All right, very good. Now, the reasons that we have labeled these as acids and bases, so this is our acid, this is our base. is that this one will donate its H plus to the solution, and the water will accept it like that. All right, let's do this one. We've already done this one. But you can see here that as we did before, we did it this way. I want to get to the more complicated examples. What you're going to notice now is that we're going to start seeing double arrows, which means that this potentially could react with this, and we get our starting reactants back again. So we're going to start looking at labeling things as acid or base on both sides of the reaction. And so this is where conjugates come in. Conjugates are the before and after result at once H plus has been transferred. So what that means is that I'm going to give my H to this guy, which means that H2O is acting as an acid and ammonia is acting as a base. But once my ammonia takes H+, here's what it looks like. Now, let's assume that the reverse reaction can happen, which it can, which is why we've drawn that. For the reverse reaction to happen, in order for me to get back to ammonia and water, I would have to pass over an H to hydroxide, which means that this is behaving as an acid, and this is behaving as a base. So what we've done here is I have linked these two substances together because they differ by H+. And we call those conjugates. So a conjugate pair is the before-after substances in an acid-base reaction for a given entity. So the ammonia starts as ammonia. Once it's taken the H+, it becomes NH4+, or ammonium. Water starts as H2O. Let's get a different color here, actually. Water starts as H2O, and then it becomes hydroxide. These differ by H+. I have removed H+ from water to make hydroxide. So they are conjugates. When you link conjugates together, you will always link an acid and a base. A base will always have a conjugate acid as its partner. An acid will always have a conjugate base as its partner. So what you're going to end up doing is you're going to be given reactions that are going to ask you, label all of the acids and bases, and then link the conjugates together. You don't have to include this H+ transfer. I was just showing that to facilitate what's going on here. But now that I've erased the scratch work that we had, everything that's shown here is what you'd be expected to write for some question regarding acids and bases and conjugates. Oops, let me leave that text up there in case you wanted to see that. So, ammonium here is the conjugate acid of NH3. Same thing that's going on here. Hydroxide is the conjugate base of water. So let's start labeling our conjugate acid-base pairs. So what I want you to do is I want you to start on the left here. We've got H3PO4 and H2O. Based on what you see, based on what you see for our result here, tell me what was the acid on the left and what was the base on the left. And then go to the reverse reaction. If these two react to form this again, what's the acid, what's the base? and then link the conjugates together, however they get linked. That's hard to do in the chat, so I'm just going to give you about 4 or 5 minutes, and then we'll go over the answer. One more minute, we'll go over the answer. All right, so how do we figure out what's what here? Well, let me get the pen out first. There's my stylus. Okay. All right, so what is passing H plus to what here? So I started with water and I ended with H3O plus. So water must have received the H plus, right? So that makes this the acid and this the base. All right. What received in this reaction the H plus and what gave it away? Well, H3O plus has to give its H plus back to become water, right? So we would say this is our acid and this is the base for the reverse reaction. And then finally, we would link the conjugates together. These two differ by H plus, so they are conjugates. And these two differ by H plus, so they are conjugates too. And then you get the answer, which looks like this. Now you'll notice that I didn't write the terms conjugate over and over because I just didn't want to write conjugate repeatedly. Conjugate is a matter of perspective, so you could put the label conjugate wherever you want to, or just assume that they're both conjugates of each other, which is why I just write acid and base all the time. All right, we've got another one here. I'll give you 2 minutes to try this one. And we'll go over the answers together. All right. So the way that I do this is I like to look at the fate of what the molecules become. So for example, when I look at H2O and I look at hydroxide over here, I know that water had to lose H plus to become hydroxide. So that means that water here is acting as the acid. I wrote B for some reason. So if water gives up its H plus, that makes it an acid. And this must be the base because it's accepting it. The end result is I get bicarbonate turning into carbonic acid. Carbonic acid has the word acid in it, so duh, right? Hydroxide is a strong base, so there you go. And now I can link the conjugate pairs together. There you go. The little, like, linky lines that I'm drawing, there's no rhyme or reason as to whether they cross over each other or don't. It's totally just a matter of what I draw when I'm writing out the reaction. So I try to randomly just shuffle what goes where, but you'll always have things linked together in pairs. All right, and so there's the answer for that one, which will clear this. There we go. Now it looks nice. All right, so we are ready for a break. So when we come back from the break, we're going to do these problems. There's the homework practice. You're going to start to see some weird acids and bases that you've probably never seen before. But the premise is still the same. Where does the H plus go? Where does it come from? Label the things appropriately. So more on that when we come back in 10 minutes. So let me get the timer on screen. There it is. It's going to tell me to update. I'm going to tell it no. You know, one of these days I'm going to update this timer, and then I want to deal with this for like a week. So we'll do that, and then I'll go get the music. See you in a bit. There we go. All right. Two practice problems on the board. One of them contains an unusual base. Ooh. But remember, oops. Remember, you can always crash into the mic like that. Remember that you can always figure out what each substance is by looking at the two substances that differ only by H+. Those must be conjugates. And then to ask yourself, okay, what happened to do this? So, for instance, up here, we'll do part of this. What happened to water to make it H3O+? Well, if water accepted an H+ over here, what does that make it? It has the H+ over here. How does it get back to being water? Well, it'd have to give it away, right? So what does that make it? That sort of thing. So that's the logic you want to follow. Go ahead and try these. I'll give you 5 minutes to do these two problems, and then we'll go over the answers in just a little bit. One more minute, we'll go over the answers. All right, let's go over the answers. So I got to do that on this page here. There we go. All right, so I'm drawing not with the brush tool. There we go. So if I'm reacting these two things together, there we go. Let's make that a little bigger if we can. All right, so here's my water. What's its conjugate going to be? Well, it's going to be this, right? Because those differ by H+. H2O would have to take an H+ to become H3O+, so that makes this the base. And this must be an acid. Over here, H3O+ trying to turn back into H2O+ would have to give away its H+, so that makes this an acid. And this is our base. And then finally, we can just link the conjugates together. There you go. For the second one, we start with water and hydroxide here again. So these are obviously going to be conjugates, and then these two are going to be conjugates as well. H2O is going to become OH-, which means that it needs to lose an H+ to do that. So that means that CH5H5N must accept an H+, and you can see that it totally does. It's this one. And then going in the reverse direction, well, hydroxide's a base. It's going to accept an H+ from this right here, and then we'll just link these conjugates together. And there you have it. Let me know if you have any questions about that. There you go. I had to get a drink of water there. All right. Now, you'll notice that if I go back here really quickly, that I had my water, and we said that this is something that water could do. Oops, I'll just throw the pen on the ground. Hold on. Water could act as a base, but it could also act as an acid, depending on what the reaction is, what substance water's reacting with. This is how you're going to be asked in the exam. Now, I can't do it quite this way in Canvas, but it'll be similar enough. So if you do it like this on your paper and then you follow the directions on what Canvas is asking you to do, you should have no problem. But you can see here that water is doing both the job of an acid and a base, depending on the context of the question that we're looking at. And so a substance that's capable of being either an acid or a base is called amphiprotic. So something is amphiprotic if it can behave as both an acid and a base in different circumstances. Never at the same time. Something can never be an acid and a base at the same time. All right. These next few examples just talk about types of acids that are available. So we have monoprotic acids that have just one H that pops off. Then we got diprotic and triprotic. And this is just the number of H pluses that these acids can donate. Now again, remember, not every H plus is acidic. Any molecule that has H's that do not dissociate, the H's are written separately. So you'll notice that all these H's are in the front. The front H's are our acidic H's. So if I have something like this, so for example, vinegar, this H is acidic, but these don't pop off at all. Now, if I have a diprotic or triprotic acid, and I do have multiple H's to make it that way, then you only lose one H at a time. So the first dissociation would be this, where this is my new substance, and then I take that, and I do it again. Oh, that would have been nice if I'd predicted that correctly. And so each step occurs in sequence. I can't just lose two H pluses at a time. There are reasons for that that are sort of beyond the scope of this class. They have to do with acid strength and how strong an acid something is, and that acidity weakens as things lose H plus because they've already given up their H plus, right? All right. In this next section, what we're going to talk about are how strong acids and bases are. And we're going to assign them terms. So there's going to be a list of acids and bases that you're going to need to commit to memory, or at least just have handy for the exam and the final. So if the exam asks you, what's a strong acid? Look at this list of strong acids, for example. All right. I hate your textbook in this chapter because it does this thing that nobody else does. I have drawn on the slides what your textbook does, and then I'm going to draw over it what everybody else does. So I'm going to just fill this in with red. And then we're going to do this. Doot, doot. Don't draw the equilibrium differently for strong acids. Just draw a forward arrow. All right. A strong acid is called strong because it dissociates completely and there's no reverse reaction. When I say that there is no reverse reaction, what I mean is that these two, even though we could say, oh, well, this is an acid and this is a base, I'm going to put base in quotes here, they don't recombine. The amount that recombines is virtually 0. In fact, it's so close to 0 that I believe that any chemist would say, yeah, it's 0. Like, realistically, it's 0. Now, this slide is saying, oh, it's still in equilibrium. The reverse reaction can occur. Yeah, it can, but it doesn't. So just ignore everything on this slide. Strong acids, forward arrow only. That's what you want to know. A strong acid will dissociate completely, which means that the reactants completely react and the products are stuck there. So if I put HCl in water, I end up with just H3O plus and Cl minus. There's no HCl left. It is all completely dissociated because HCl is a strong acid. All right. Here are the strong acids that you care about. These 7 substances. HCl, HBrHI, HNO3, HClO3, HClO4, and H2SO4. I honestly don't really like the inclusion of this one. This one's kind of like, yeah, it's strong-ish, but it's not 100% dissociation strong. So, but your textbook lists it, so we'll just go with your textbook, even if it's wrong. Any other acid is considered to be a weak acid, and what that means is that when you put it into water, not 100% of it dissociates. Only a small amount dissociates. So we write that not like this with the stupid short double arrow. Let's get rid of this. This is dumb. Nobody does this. Frickin' Stoker. Here is instead what happens. And we'll draw it in green, I guess. We draw the double arrow for equilibrium. So don't worry about the teeny tiny short backwards arrow or forward arrow or whatever. Just draw a double arrow. A double arrow means that the reaction is in equilibrium. So again, ignore this. This is dumb. What are the strong bases? The strong bases contain hydroxide. And so that's going to be any compound containing hydroxide and a metal from either group 1 or 2. Now you'll notice that not every metal is included here. So for instance, excuse me. Magnesium hydroxide is not in here. Neither is beryllium hydroxide. The reasons for this is because those hydroxides tend to be insoluble, whereas all other hydroxides are soluble. So if it's insoluble, it can't act like a base. It just stays as a solid and nothing happens, right? So this is another one of those you kind of just have to know which ones are the strong bases. I just noticed that this has a typo in it, and I have no idea how long this typo has been here. Forever, possibly. All right, so what would the equilibrium? Equilibrium. I'm going to fix that right now because that's going to just annoy me. Let me find it. There it is. What would the equilibrium be? There we go. We'll see if oh, you know what I should do. Save. I really hope it didn't just save all of my ink annotations. Hopefully not, otherwise I have a lot of deleting to do. Anyway. What would the reaction equilibrium be between ammonia and water? So, because ammonia is not a strong base, we would do this. And so we would say, well, ammonia is going to react partially with water. And we'll draw a double arrow for it. So really, this section is about what's the correct arrow to draw for strong and weak bases. Strong gets the forward arrow. We'll write it like this. So strong reaction gets only the forward arrow. The weak reaction gets a double arrow. And that's really all you need to know. All right, and so there's the homework practice for this section. Now, up above is a listing of some just factoids that might help you assign acid or base to conjugates, for instance. The conjugate of any strong acid or base is going to be neutral. So, for instance, if I did something like this, and I said, okay, this is a strong acid, this would be the conjugate of it. But because the acid is strong, this can't be a base. If it was a base, it would pick up its H plus and turn back into HCl. So it's actually just neutral. We call it a, quote, base for the purposes of conjugates. But as far as we're concerned in a solution, Cl minus does not act as an acid or a base in any way. It just hangs out. It's neutral. So if you're working with strong acids and you're asked to label conjugates, you could still label them as conjugates for the purposes of linking two things together. But for a more complete description of acidity and basicity, the conjugate of a strong acid or base is neutral. All right. This might be the last thing that we have time to do today. Probably, yeah. I mean, we have, what, 20 minutes? Okay, so yeah, let's neutralize some reactions. So the next step is to take everything that we've learned about acids and bases, and we're going to start writing balanced equations with them. The most common reactions of acids and bases result in two things, and one of those things is salt. You know what salt is because you eat it. Sodium chloride is called table salt. I can't believe I misspelled that. Table salt. I don't know what I was going to do there. That's the highlighter. Oh, I hate this pen. There we go. Now, salts are not specifically just ionic compounds, but they are ionic compounds formed by acid-base neutralizations. At least in this context. So what that means is that if I react an acid and a base together, I will create a salt. The other thing that I make is water. Now, the constraint here is that my base must contain hydroxide in order for me to get water out, because the acid will neutralize the base to produce water. So when we're doing an acid-base neutralization, the first task is to find water. Can I create water from the acid-base neutralization? Once you have done so, everything else must be the salt. So let's see this practice in action here. All right. So for our first example, we're going to neutralize sulfuric acid with potassium hydroxide. So here's what we're going to do. We're going to start like this. And I'm going to do this. Blank blank plus blank blank. The blanks in the front are coefficients because we got to balance the equation. But we need to predict the products. The first product we're going to predict is always water. Can we find the water? Well, let's dissociate these substances. So I've got H2. So I'm going to split off both of my H pluses. I've got sulfate. And you'll notice why I'm writing this backwards in just a second. Then over here, I've got potassium hydroxide. I'm also going to write this backwards. Like that. Because now here's what we can do. I found water. There it is. However, I need more hydroxides here to neutralize out this guy, right? So if I put a 2 here, then I can do this, right? And then there's my water. I have neutralized all the acid and base. Everything else is the salt. So we just write that. There you go. You've neutralized an acid-base reaction and predicted the product successfully. So to summarize what we did, step 1, find water. And then neutralize all the H plus and OH minus. And then step 2, add extra acid and base as necessary. And then step 3, everything else is the salt. And then step 4, enjoy. Because we like doing that, right? So follow those steps, and you'll be able to balance any acid-base problem. So I'm going to give you one to try. We're going to start with this one. Well, actually, no, you know what? I'll just put all of them up on the board. I didn't mean to go that far. There we go. I'll just put all of them on the board. So I want you to do... I'm going to go over the first one in about 3 minutes, and then I'll give you more time to do the rest of them. So the second one is similar to what we just did. The third one is more challenging. So go ahead and try these acid-base problems. I'm going to give you like 5 or 6 minutes to do them. You know, I don't want to interrupt you, so I'm going to let you try to do these on your own. You've seen an example, so it should be okay. We'll go over all the examples together in about 5 or 6 minutes. So see you in a bit. 1 or 2 more minutes, we'll go over the answer. All right, let's go over the answers here. Oh, perfect. Look at that. So, I don't know why that moved. Oh, it's because I hit that button. Okay. So we can predict the products here by dissociating stuff and then looking for water. There it is, and I've actually neutralized all the water, so this is done. Everything else must be salt. And so there you go. That one's nice and straightforward. This one is just like the one that we did previously. And so let's look for water. So I'm going to put the water on the inside here. So there's my H plus from H2SO4. So if I split it off twice in 2 separate reactions, this is what I will get. There's my rubidium hydroxide, so we can make water. That part's good. But I need another hydroxide here to react with this, so I got to put a 2 here. So that this happens. Now I can react this water, make a second one. And everything else is the salt. There you go. And then the last problem here. This one's just kind of obnoxious because we got to go back and forth over and over and over. All right, so I'm going to split off all my H pluses for my triprotic acid here. And then we will do our hydroxides for our calcium hydroxide like this. So there's our pieces. And you can see here that we've already made 2 water. But I need 1 more hydroxide and they come in pairs. So it's like, oh, great. So I'm going to do this. First of all, I'm going to change this number, so I'm just going to leave it as blank right now. So if I do another calcium hydroxide, I get this. That's great for this one, but now I need more phosphate. So I got to do this. H plus, H plus, H plus. Oh, look, we're going to need another one over here. So that's great and all, but now I got to do this. And then, oh, look, we found all the water. Excellent. So there's a water, and there's a water. What's the rest of it? Everything else is the salt. We get calcium phosphate, or calphos. All right, so that's how we neutralize acids with hydroxide-containing bases to form water and a salt. All right, there's the homework practice for this section. That's all we're going to have time for today. We'll introduce pH on Thursday. There are some basic calculations that we'll be doing with pH. We're going to talk about buffers, and then that's it. One of the sections I will probably skip. We'll probably skip the salts, acidic and basic salts section. Just not enough time. All right, well, that is all that we have for today. So I do want to thank everybody for coming out to the lecture. Make sure that you are staying on top of the stuff that is due this week, because there's a lot of it. Go do quiz number 8 tonight and quiz number 9 tomorrow if you can't do them both tonight. Just make sure that they get done so that when the answers are released, you'll have scores for them. Exam number 2 is on Friday. Make sure to get an email in to me if you need me to move your exam date. And then next week sometime is the final. So we're almost done. Yeah, that's all I got. Have a wonderful rest of your day. We'll see you on Thursday. Take care.